Good morning, everyone. Welcome back to the ESA webinar series powered by our good friends at Situ. Hope everyone had a great long weekend, Canadian long weekend. Got a chance to enjoy some gardening and outside activities while still practicing our safe physical distancing. Just a quick couple housekeeping before we get started. Reminder that the presentations and recordings are available later in the day at www.esa.org/webinars. Also a reminder that we've converted Envirotech to a virtual event with 27 presentations over 2 days and 7 webinars, June 11th and 12th. Encourage you to register and support ESA, your industry association, your fellow presenters. We've intentionally kept the price low. It's only $49 for members and $79 for non-members. So please register. We'd greatly appreciate it. And now on to today. We have Andrew Pisoni and Todd Harrington from Regenesis, both down in the US, speaking today about recent trends in situ hydrocarbon remediation. So the presentation is about 40 minutes, and at the end of their presentation, we'll do the usual question and answer period. So I'm just going to switch over control to Todd and let them take it away. So Todd and Andrew, you should have control.
Second here.
Yeah, and I'll join you guys back at the end with questions and answers.
So while Todd's getting up, just want to thank everyone for joining us today. We really appreciate you taking your time out of your day to listen to us and engage in this presentation. And thanks so much to Joe and ESA for setting this up. We appreciate the chance to share our technologies and share what we've learned and get a chance to interact with everyone, even though we're a little farther away than we normally would be. So today's presentation is called Recent Trends in In-Situ Hydrocarbon Remediation, and focuses on treatment with activated carbon remediation fluid. I'm going to just give a quick intro. My name is Andrew Pisoni, for those of you who don't know me. I'm the Northwest District Manager for Regenesis. So all of you in Western Canada, I would be your point of contact for Regenesis. My role is outreach as well as design. And then Todd Harrington. Todd recently took up Global Petrofix Product Manager for Regenesis. So Todd used to manage the West region, but we came out with a new product that is kind of taking the market and taking Regenesis's capacity to manufacture by storm. It's been extremely popular. It's called Petrofix, and that's what Todd will be talking about. So for those of you that don't know, just a quick intro to Regenesis. If you're not familiar with us, I'm sure most of you are. This is just one technology we offer, Petrofix. Like I said, it is kind of booming in both the US and Canada, but we also offer a whole suite of other reagents, ISCO, ISCR, various biological reagents. And I just wanted to point out also our other groups. We have a large group called Land Science Technologies, a sister company of Regenesis, that specifically focuses on vapor intrusion, both pre and post construction. Todd and I would be mostly part of the remediation technologies, although we also kind of fall into the research and development groups, which is probably one of the most robust, if not the most robust in the industry. And then remediation services, we don't offer these in Canada necessarily, but we do still offer the support that of all the lessons learned from us actually getting in the field and implementing our own products. So this slide, I want to just say how it kind of differentiates Regenesis. Personally, prior to coming to Regenesis, I've been here for about 2 years. I worked at various remediation implementation companies and have kind of used every reagent under the sun. And I would say Regenesis differentiates itself with, I would focus on the reactivity and ease of use. And so for reactivity, I'd say Regenesis products we in general look for how is this product going to interact with the subsurface, not just the target chemicals, so your hydrocarbons, your chlorinate, but how is it also going to interact with everything else in the subsurface? And then how is that going to affect its persistence, as well as degradation of compounds? And then in ease of use, I'd say there's no other company that focuses on how easy it is to get our reagents to the ground, and how are the actual field folks going to be able to use these. Is it going to be difficult, and are they going to stay? And then that in turn greatly affects distribution, which is something that Todd will talk a lot about today. So Petrifix in the middle is going to be the topic of today's focus. But I want to quickly mention Plume Stop. A lot of you have probably heard of Plume Stop. It's been a great success at Regenesis. It's kind of been a game changer in the environmental industry. So what brings all of these reagents together is both their colloidal nature and their small size. These reagents are all about 1 to 2 microns, the SMCVI being a little bit larger than that. And that size is about the same as a red blood cell. And what that means is that it's much smaller than your average sand particle, and even smaller than many silt particles. So when one is placing this in the subsurface, you're not moving anything out of the way. You're basically finding space within the natural pore volume and not changing the hydraulic characteristics of the flow paths, but in placing something that's going to be there for a long term and interact with whatever is flowing through there. Todd will differentiate Petrifix and Plume Stop, and we weren't going to talk too much about SMZVI, which is a form of zero-valent iron, which would treat chlorinated solvents. But I want to mention one more thing that ties these together is their colloidal nature. When you think about a colloid, it's basically a type of suspension. For example, milk is a colloid, and this is basically allows these reagents, which otherwise would agglomerate or not necessarily move in water, to act like an ink. So both Plume Stop, Petrifix, SMZVI, they are all miscible in water, and so when they're injected, they can easily flow. So now Todd's going to talk about Petrifix specifically.
Great, thank you, Andrew. Appreciate that. So yeah, I want to get into what's new for us today. It's certainly new for Regenesis, new for the market on treating hydrocarbons. My background when I first got started in this industry was working at the US EPA at the University of Cincinnati on oil spill bioremediation research. So that's where I started. It's somewhat exciting to me to come back and work on a product that specifically addresses hydrocarbons again. I feel close to my starting roots in this industry, and it's been exciting. I'm going to get into, as far as an outline today, of what the core technology is and what differentiates it. And then I'm going to get into some on Petrifix injection practices. I think that it's easy to talk a lot about products and not give a little bit of information on how to get those products into the ground successfully. I'll touch on that briefly. Certainly, I want to get into some case studies that we have for Petrifix, and then I'm going to get into some of the resources and the design assistance ability that's online that you can access this technology through. And then we should have plenty of time for Q&A. As Andrew said, Petrifix is a result of our colloidal research. It's really been the cornerstone of Regenesis as colloidal reagents. They're not so small to react too soon, and they're not too big that they can't travel in the subsurface without high pressure fracturing, and Petrifix fits that. It's a carve out of a technology that we've had for a number of years called Plume Stop, which launched in 2013. It's been applied on well over 500 sites, and really an industry product for solvents, PFAS, and hydrocarbons. The challenge that we had is that people wanted to use it for hydrocarbon sites, but many times the amount of hydrocarbon or dissolved hydrocarbon mass that we have at sites would overwhelm the amount of carbon for, say, Plume Stop that we had. Here in Denver, Colorado, where I live, we have a lot of glacial tills. We have a lot of really heavy-duty hydrocarbon sites. I ended up having to turn down more Plume Stop related hydrocarbon sites than I desired to, and we really saw a market for that. And we evolved a product called Petrifix, which uses the same type of carbon that Plume Stop does, but it's been formulated specifically for hydrocarbon sites. So for instance, what we want to do with this technology is the same that we saw when we treat solvent sites with Plume Stop. We want to see fast results for petroleum sites. We want those results to persist for years and years if possible versus, rebound after the first quarter or two. We want to be able to have higher treatment ranges, and we want to be able to promote destructive biodegradation after we sorb the contaminants, and if we can make it safe and easy to apply. And I think what's unique, actually do it yourself, that's what we wanted to do with Petrifix. Specifically, what's in it, I want to get into that so everybody knows what the core chemistry and fundamentals are. It is the use of a micron scale activated carbon. Now, micron, in terms of the diameter of the particle, and I'll show you an image here shortly, is 1 to 2 micrometers in size. For reference, that's the size of a red blood cell. We co-mix the product with nitrate and sulfate electron acceptors because we want to co-stimulate, or we want to biostimulate anaerobic biodegradation, and quite frankly, we just needed something that would flow with a liquid material, and those can be dissolved in water. So these treat BTEX, TPH gas, TPHD, MTBE, naphthalene, all the usual suspects. It is easily and usually preferred to be injected with direct push for low pressure uniform distribution, but it can be injected into wells, and it can be injected into trenches and excavations, and I have some images on that coming up. As a qualitative rule of thumb, we feel that sites that have persistent standing free product are probably too much to use Petrifix. You're probably looking at some sort of a mass reduction approach there, followed possibly by Petrifix polishing at that point. The formulation itself, when it's shipped to your site, is plus 30% carbon by weight. That material is shipped currently only in 55-gallon drums. And within that 55-gallon drum with the liquid carbon in it is less than 10% calcium sulfate dihydrate. That calcium sulfate is added both as an electron acceptor and a stabilizer for the material itself. Each drum of Petrifix ships with electron acceptors, your choice. You can order a bucket that is a 50-50 mix of ammonium sulfate and sodium nitrate, which we think is the most efficacious. Or if nitrate is of concern to you, per local regulations, you can order a sulfate-only blend of electron acceptors to add when you mix everything together. As far as adoption to date, Andrew mentioned the success. I don't think we expected Petrifix to grow as quickly as it has since September of 2018, but currently we've been on over 129 sites worldwide. That includes at least 6 projects in Canada. The reason I can't quite look them all up is because we used to sell directly through our distributor Brenntag, so I did not always have visibility on where it was going, but it's at least 6 products in Canada. And because of the materials in Petrifix, which is simply an activated carbon and electron acceptors and water, it's a really simple UIC process to get approved. It's an easy product to understand. So let's get into a little bit of modes of action. Many of you have used activated carbon and you're somewhat familiar with it. So the first mode of action of this is actually the sorption of contaminants. And the way this is done is that once we inject Petrifix as a liquid, it coats the soil surface with a thin layer of carbon, and then that sorbs contaminants out of the dissolved phase onto the Petrifix. So this image on the lower left we've shown for years, but it is an image of a sand particle. The sand particle is probably roughly around 60, 70 microns, micrometers wide. And notice the flakes on there. Those flakes are Petrifix or could be plume stop particles that are attached to the surface. I like this image because you can see the openings between the soil. And I want to make the point, and a lot of people ask, does this clog an aquifer? It doesn't clog aquifers. This coats it like a thin layer of paint and leaves, large openings through the aquifer, conductive pore space for water to go through. So once in place, what happens, and this cartoon shows that you inject the Petrifix and it goes through an aquifer like a black liquid, hopefully flowing through every available pore space structure, and then it coats the soil like it's showing here in the cartoon. And once coated, as contaminants shown in red enter from the left, they come in, they hit the surface of the soil where the Petrifix is at, and they're sorbed that contaminant. importantly, contaminants that are say clays or silts that are then coming and back diffusing out of tighter soils will be captured by Petrifix. Petrifix is ideal for the control of back diffusing contamination from sites. So once absorbed to the layer of Petrifix, the soluble electron acceptors that we've included, nitrate and sulfate, they definitely kickstart bioremediation. They enhance syntropic remediation. Bacterial colonies will actually go around and incorporate Petrifix in the biomass. And as those electron acceptors are utilized, the benzene, the TEX, the TH gas, diesel, et cetera, are biodegraded from those, from Petrifix, which actually generates the material itself and allows that activated carbon to have an even longer lifespan. So it's a somewhat cyclical process where you can cause regeneration of the carbon. The selection of nitrate and sulfate was intentional. Not only was it designed so that we can have a water-soluble form of electron acceptor, research in recent years has shown that when using multiple electron acceptors, you can promote a syntropic effect. And for instance, nitrate through research has been found to be better for the stimulated biodegradation of benzene. Sulfate, on the other hand, they are more slow in reducing hydrocarbons, but they're versatile and they can coexist with methanogens and are a really important microcommunity to promote. So what you do ultimately have is one of the things that has been overlooked, I think, as we've done natural attenuation research over the years, is on the lower left, we see the image of the electron acceptor order of thermodynamic preference, starting with oxygen on the right, then moving to less thermodynamically favorable electron acceptors to the left, with methanogenesis being the least preferred and thermodynamically preferable. One of the things that I think we've overlooked a lot is the fermentation of hydrocarbons. So by adding multiple electron acceptors, you're actually able to help kickstart syntropy, which actually includes the fermentation of hydrocarbons, which actually does a lot. The fermentation and methanogenesis hand in hand do a lot to get rid of the mass out there, and that is the subject of the research that's been out there. And I've listed 2 papers that we talk about that with, and we've actually documented some of this in a technical bulletin that we have that's available for you to download from our website. So that's a little bit about the science behind what we're doing there in promotion of biodegradation. Moving on a bit, I think it's important to spend some slides on why it moves in the subsurface and how to get it into the subsurface. There is an advantage to being 1 to 2 micrometers in terms of getting it into an aquifer. Andrew alluded to the fact that this isn't just suspended carbon. We've actually formulated it in a way that it doesn't stick together. A lot of times if you take, or most of the time when you take powdered activated carbon or ground activated carbon, you mix it in water, it forms somewhat of a slurry, and that slurry must be fracked. There's typically no way to get that into the groundwater versus high pressure. So these images here on the upper left is a image of a granular activated carbon pile, and the size of that is typically 400 to 1,000 microns in diameter, or roughly the size of a sand particle. That definitely takes many, many hundreds of PSI to get it into the ground. Powdered activated carbon, on the other hand, typically ranges from about 50 to 250 microns. Again, the particle size itself, or even putting it in a slurry, it cannot overcome the need to be high pressure factored into the subsurface. With Petrifix and plume stop technology, with Petrifix, because it's so small, because it's formulated not to stick together, it injects like an ink. So typically the pressures are below 60 PSI. Occasionally I'll see 80 or 100 PSI, but that's rare. And it's controlled, which means less surfacing and more placement where you need it, which is it's really the conductive zones of an aquifer and surrounding the silt, surrounding the clay from floor to ceiling, and it leaves really no escape. Some images on that of an aquifer seam fracture versus an aquifer flooding. On the left would be, say, in the emplacement of a carbon, a powdered activated carbon, in roughly about a 1 centimeter seam fracture in clay on the left. It can also impact monitoring wells under high pressure, where the material can sort of pressure jet into utility corridors or wells, which is these wells are unable to be fixed and they have to be replaced, and it can compromise those. Low pressure placement of carbon, I like to use the word flooding, and it will go through a conductive zone. And when you see the images on the lower right, what this is a soil core. And this soil core has interbedded layers of silt and clay with sand. And you can see on the lower right, on the lower two cores, which is the aquifer interval that we're injecting into, the petrifix going into sand and the petrifix going into more of a coarse material with a layer of silty clay in between where it did not go. So, you know, radically different from seam application of the material, which gets me into a concept which is a little bit newer for the industry. Is one way we like to put, or we recommend as a tip that people put in petrifix, is not through the typical tool tips, bottom up, or pressure activated tool tips typical from, say, GeoProbe. We recommend the use of long multi-port tips to straddle conductive zones and low pressure flood into them. I'll show you a picture in a second, but the size of these typically are 2 to 3 feet or maybe a meter that you can get them. They can be used top down or bottom up. And when you inject them into the subsurface, I like to think of them acting almost like straddle packer, that you can have mixed geology where you have full centimeters zone, you've got, you know, interlayered then by some, you know, say clay, and then another sand zone. You get those effectively. If you use it like this, using low pressure, you can let petrifix find the path of least resistance. It works very, very well. And that's what we like to use. And I'll show some pictures of those tooltips in a couple more slides. The most common applications of doing this type of injection is source treatment, just to knock out the source area of a plume, or expanding out of the source area and hitting the main body of a plume. That's probably the #1 technique that we're seeing with petrifix. We see, to I think our surprise, we see a lot of people wanting to do a barrier. So this could be in combination with source treatment. The idea here is that we have contamination heading towards a property boundary, heading towards, say, a stream or a water well, and you need to put a wall there that lasts years, and petrifix will fit that bill. Another big area is people have been spray applying this into excavations to give them that insurance policy that when they go to the expense of excavating contamination, they can spray apply petrifix on the back end and add that as a barrier, something to soak up and polish.
Hey Todd, can I just say one thing about that last slide?
Yes.
So this is something we see very commonly. You know, you can think of the building being as the source of contamination. So you have a UST under that or something like that. You know, in Canada, excavations are extremely popular. Dig and haul, you know, just remove it. There's lots of land. But in a case like this, where you may have contamination under this building, petrifix is a great long-term treatment for anything that may be coming off that building that you weren't able to access due to that utility or due to that structure being the way. So this is something that in the States has been extremely popular over the last year or two.
That's a good point. I mean, you can see that was an issue here. They're right up against the foundation of that building, and they sprayed pretty heavily on the sidewall and the base. Thanks, Andrew. All right, so let's talk a couple slides on injection practices. So we already saw the cartoon that showed what happens when you use what we call a multi-port tool. The tools on the right, the tool on the left actually is a top-down tool, and the tool to the right of that is a bottom-up tool, but they're both multi-port tools, each about 3 feet long. And I leave that up to your driller, sort of the skill of your driller, the geology of the site. You know, we can get into specifics on that more, but these are very effective on most sites to get the product in the ground under low pressure. Less surfacing, more controlled. Typically, we can see 2 to 8 gallons per minute per point in most sites. And then one of the great things about petrifix, and this is just something that I feel very strongly about, is that I feel like product distribution has been the Achilles heel of our industry for in situ of every single product. And I feel like we spend a lot of time working on the chemistry and working on good designs and good layouts. And then we inject largely sight unseen in the subsurface using various techniques. And most of the time, if we don't get the results, it's lack of distribution, pure and simple. And having worked at Regenesis for 16 years, I felt the pain over and over on that. One of the nice things about Petrifix that is very helpful is it's simply its own tracer. And what I recommend for people to do on every injection is that they inject, and then on day one, and they inject a couple points, and then they take a soil core between those points, and they look for Petrifix and try to see if they're getting distribution. If not, it's time to make routine adjustments, possibly increase volume, increased or even decreased pressure, possibly change the size of the injection port, etc. Of course, this can be done before the actual application, but it also can be done if you're prepared the day of. And I think to lock that in really makes all the difference in the world. These soil cores that I took on the right, we did exactly that. And then we really locked it in, and everywhere we took a core on this site on the right was showing this terrific distribution. So given the time, I'm going to transition into some case studies, and I think we're doing well on time here. So you can see some of the results. These slides I'm showing you, this is a lower level benzene site, but it's an important site because it's a site where ISCO was done, and then it was wrapped up with Petrifix, and actually it was just uploaded to our website about a week or two ago. This was done at a DoD facility, actually with Scott Air Force Base in Illinois, and contamination occurred at this refueling area as a result of a UST storage tank that linked on site. A couple remedies were used over time to clean it up. The first remedy actually was what we call an ISCO bio approach. It's where you use an interstitial chemical oxidant, and then you polish that and you co-inject with something like an oxygen releasing product to stimulate aerobic degradation as a polish. That was done a couple years ago, but it still didn't achieve closure levels that we needed, and Petrifix came out, and the client, which is AECOM, actually went forward and used Petrifix on that. So the initial Regenox ORC advanced injections occurred with direct push early 2018. Petrifix was applied 1 year later in early 2019. As far as results go, it was successful at the end of the day. This chart to the right shows probably more data than I need to show, but it shows from 2013 coming in. We had steady benzene concentrations up until early 2018 when we treated with Regenox and ORC. We did see a reduction. We saw, maybe around a 50% reduction. And then we realized that, or the client realized that they were going to need more of a polish, more of a technique to handle this. And so we came in with Petrifix and injected that. We've actually had 5 consecutive monitoring events at non-detect. This site actually hit for no further action status following those events. So the client is very happy. We have a case study up on that, and I think they're going to do a client spotlight here coming up shortly. For low concentration sites, I think, to me, I'm getting a little biased. I mean, to me, these are fantastic results, but these are the results I expect. Here's another site in Florida. The reason I'm showing this is one of the oldest sites that we have, and it's a site that started a pilot and went full scale, and we're waiting full scale results. But we injected on this one in early 2018, and on this one as well, we had 5 consecutive monitoring events at non-detect where everything was pulled out of the dissolve phase, and the BTEX and TPH gasoline were fully biodegraded. The client took those results, the amounts that we injected, and just upscaled that to full scale, and full scale occurred in January of 2020. We should be getting results back here shortly, and everybody's expecting something similar. So those are low concentration trends. So what about something a little bit more, or more high concentration? This site that I'm showing you, we have talked quite a bit about. So if you've seen other webinars by me or other people, you've definitely seen these slides. This is a site that we did in Indiana. It happens to be a really good client that we had, and this client's probably done 30 or 40 sites over the time that he's worked in consulting. Really good client. He got wind of Petrifix early on and asked to do a beta test. We were happy to do a site. The only issue we had with the site is we were concerned because it was rather high concentration. We hadn't tested it before that high. Everything was new. So you can see here the BTEX, TPH gas, and diesel when added together is over 50 milligrams per liter. I would consider this hot, in my book, for a site like this. This had gone through El Napo recovery in the past, ASSVE, but they still had quite a substantial plume. Okay, let me go back real quick. What we did for the pilot test is we actually picked a point in the middle of the plume. We didn't go in the source area. We didn't go on the down gradient toe, but right in the middle. The image that says treatment area on the right is just showing almost like a little postage stamp size thing on the white background, where things are flowing from the former facility on the bottom and going upwards towards the top of the slide towards this treatment area. So the idea is here is this pilot test is a temporary pilot test, and we would expect it to probably rebound after time because of the constant influx of contamination. We injected 2,000 pounds of Petrofix. We chose to use the sulfate and nitrate blend. We did 12 points. We injected from 15 to 22 feet below ground surface. It was a mixed soil. There was definitely some silt out there and sand. And the spacing that we used was typical spacing, which is about 5 to 7 foot on center spacing for this site. We did take cores. We documented they were getting distribution and flooding, so we felt comfortable with the volumes and pump pressures and everything that we're using. The results indicate that starting with gas and diesel, we got some really nice, significant, and sustained reductions out there. So, one thing you'll notice is that TPH gas went non-detect for 3 consecutive events. It did start to come up just under a year later in February 2019, dropped back down again, and then went back down to non-detect. We think it's holding. It's probably right at the, it's just right there where we had enough carbon and electron acceptor just to hold it to where it's at, whereas TPH diesel range got a nice reduction, but it didn't go all the way to the floor like TPH gas did. BTEX had a similar response where it dropped and we saw really good reductions, even though it's not all the way to non-detect. We're talking 94.5% reduction to date. And then the client actually went full scale based on these results in around May of 2019 or early 2019. So this will be the subject of a future presentation. He has a growing amount of full-scale data that he was going to present at the Patel conference this year in Portland, Oregon, but that was canceled. So probably what we'll do is we'll publish something before then, and I can update you on the full-scale results down the road. But really, really good results. This was a study that we also spent some extra time in because, we wanted to document in some way that biodegradation was occurring. And the way we did that is we measured for the longevity of the electron acceptors, and we looked for methane as well. And the idea here is that the nitrate is thermodynamically preferable over sulfate, and you should see that go first. So if you look at the upper right chart, that's exactly what we see. This is a chart that shows dissolved concentration on the vertical axis and time on the horizontal axis. And the green line is nitrate concentrations. And what you see is that increase after injection, and then essentially was non-detect, we think, in about 30 days. It was used very quickly. The sulfate itself largely kicked in after the nitrate was depleted, and we see that it was gone after about 6 months. We do see sulfate start to kick up in May, and we think that is the leading edge of the full-scale application that the client did on the tail end of this. We were excited to see an increase in methane out there. I want to mention that there already was methane. So when I mention methane, I don't want people to be concerned that we're generating a lot of it here, but it is an indicator of biodegradation. So we went from a background of roughly, say, 2 milligrams per liter, and then it did see an increase to about 3.5 to 4 milligrams per liter. And this methane generation stayed increased after the depletion of electron acceptors in November of 2018. We think that this is indication of that syntropic effect where sulfate and nitrate can actually stimulate a fermentation methanogenesis cycle that we think persists past the depletion of electron acceptors for the continued biodegradation of hydrocarbons, and we're starting to see that here at this site. We also did a quant array petro data. We wanted to see if there was any gene indicators at the site. We partnered with Microbial Insights for this study, and you get a lot more data than what I'm showing, and so I simplified this chart. But what we are seeing in red bars is the total U bacteria, and what we see is we did the injection. We do see a suppression after the injection in August where concentrations were down, and then they bumped up and grew over time and actually exceeded the pre-injection concentrations about a year later. Interestingly, the green bars and the blue bars are also important because they represent the sulfate reducing bacteria, and you definitely see the stimulation of those bacteria significantly, actually, up to a year past that, including the blue. So PM1, even though we weren't after MTBE, PM1 is a bacteria capable of biodegrading MTBE. So we were pretty excited about these results. Just wrapping up, and then we can get into Q&A on this, is that I didn't emphasize this a lot at the beginning, but one of the things is unique to us and actually to the market with Petrifix, it's really the first time that we've tried in probably 15 years to give the public an ability to design their own designs online. Regenesis used to do this with software back in the day, but it was challenging back then to do quality control. With an online experience, we're able to put training videos and design the software in a way that it guides people safely through performing an online design so that the output they get, I think, is meaningful and safe. And so Petrifix is unique. It's the only product that Regenesis has, and it's really the only carbon product on the market for in situ remediation that one has the ability to do their own design. So this allows you to get everything you need to put into a work plan and to output it, say for drilling estimates, when you need it. And it usually takes less than 15 minutes to get that. So feel free to check that out. I want to point out, though, that this isn't entirely an online experience, that I'm here as well as other engineers and geologists for full customer support. We also do a lot of offline designs and just consultation with people talking about their sites. But we do recommend that people try the online software first. Also within that are injection instructions. We're trying to make this as turnkey, I'm sorry, that's not what I meant. We're trying to make this as self-applicable as possible, that a person feels that they have the resources to take this product and inject it successfully, get the right tools. So we've created instructional videos on the tools that you would need, mixing injection instructions, how to document distribution, that's all there. There's ample application instructions available to you, including direct push application instructions, well application instructions, and excavation application instructions. We want this to be easy peasy for everybody out there because we think it's really easy to apply and you're going to get great results. So with that, I think that successfully we're at 40 after, and that concludes my part of the presentation. And Joe, I'm happy to open this up for Q&A.
Great, thanks Todd and Andrew. And Regenesis, as always, if you have questions, please type them in the question box and I will get to them as quickly as possible. In case study 1, what were the soil concentration results post application of Petrifix?
So in the first study at Scott Air Force Base, we don't have that information. That might be in a report. I'm not sure if it is, but we didn't have it. So that is something that I want to mention about Petrifix. So Petrifix is a groundwater treatment technology primarily. The reason I say that is that it does treat both soil and groundwater, but it's not designed like chemical oxidation is designed or excavation is designed to get rid of extremely high contaminant concentrations, say 10,000, 15,000 milligrams per kilogram. So I realize that may be a cleanup goal for many of you, and I would say if your cleanup goal, you need to start from 10,000 to 5,000, and your specific cleanup goal is for soil, Petrifix is probably not going to be able to treat that soil to those levels for you, and you need to work with Andrew to come up with more of a mass reduction technology. But for those sites where you're primarily concerned, even with some high background soil contamination, the movement of that groundwater plume and getting rid of it with a lot of certainty, that's where Petrifix works really, really well.
Similar to Plume Stop, I like to think of Petrifix as immediate risk reduction because you're taking contaminants out of the phase that they're most available, groundwater.
Okay. Subsurface in situ biodegradation is a slow process, particularly in Canada, where average seasonal soil temperatures are between 0 and 10 degrees Celsius. How long should one expect it to take for the hydrocarbons absorbed to the Petrifix to degrade? Weeks, months, years?
That's a really good question. Thank you for that question as well. In the first one, my answer to this is you're absolutely true. That's true. The good thing about Petrifix is that you are pulling out the dissolve phase and making it positionally, that contamination positionally stable. So you're essentially stopping it in its tracks. So whereas things might be a little bit slower with biodegradation, and particularly so if you're using nitrate and sulfate versus oxygen, it may take longer, but at the end of the day, you're going to biodegrade it and it's not going to go anywhere anyway. So you can hold it in place and biodegrade it. And so I think that's kind of the biggest takeaway with what you're going to get. I could say incidentally, I presented a paper many years ago when I did a lot of natural attenuation research. And on the scale of months and not years, the natural attenuation rates, a lot of sites in Alaska actually were comparable to other natural attenuation rates of sites in, say, Canada or the US, in terms of with respect to, plus or minus several months. And so I feel that at the end of the day, I think it's still going to be very robust. You're going to see some pretty fast results with this technology.
What we've seen in very cold weather sites, I'm thinking of the sites, one site specifically in Canada, another site specifically in Alberta with both the Petrifix, was that the colloid took a little longer to break. So there was some discoloration in the water, which can offset the concentrations of the samples. And that was after, I believe, a quarter of monitoring. In the second quarter on both sites, we saw the Petrifix disappear. Contrary to other activated carbons, the grain size of Petrifix is so small that it can easily flow in and out of the well screen. So that's not something you have to worry about, it typically being compromised. But if you do have a sample, and this is in the sampling guidance, that is dark enough that you can't see through it, likely the sample is going to be biased due to the activated carbon and the hydrocarbon that may be on there. But to answer the question more directly, I think Todd did a good job of it. But typically, either by first or second sampling, we see results.
Okay. Does Regenesis help design the treatment in addition to selling the products?
Yes, that's a good question. So yes to both. So you can self-design your own product, or you can call us for help, and we'll go either way. I think the software that we have online is really good for a corner gas station level or size of site. And so, we feel pretty comfortable with most sites are going to come out with spacing and numbers that are palatable most people. I do frequently get sites where people have many thousands of square feet or square meters that they need to treat. Those sites are probably not appropriate for the online software. It doesn't have the flexibility, and we'll do offline designs for people and consult with people. Absolutely.
Okay. Can this technology be used for as a preventative measure, applying to pipeline trenches or around pipelines to prevent groundwater contamination in case of a spill?
Yes, absolutely. I would. Yes, we've had customers do that. I've got a customer that's about to apply Petrifix in the actual tank basin gravel around it, and an active tank as a something to clean up and a preventative measure. We've had people look at putting this into trenches. So anything, I've had people put this in horizontal piping above an excavation and flood into the excavation. So think of using Petrifix as you would a liquid, and you can accomplish actually most things by whatever piping or infrastructure you put in.
Okay. And someone said, if I'm not mistaken, sulfate concentration shown in one of your slides were well above guidelines. Have you had any issues with regulators in Alberta relative to increasing groundwater dissolved sulfate concentration above guidelines?
Yeah.
In both Alberta
ahead,
and British Columbia, we have not. Those concentrations typically stick around for a few months, and then usually by a year we'll return to baseline as natural processes take over. So we haven't, and in fact, not in Alberta, in British Columbia and in the states, in Washington State specifically, we've had injections adjacent to waterways. One of them, British Columbia, was just adjacent to a bay, and then a couple in Seattle were just adjacent to rivers, and we have had no issue with the regulators. There is definitely a possibility that Petrofix could get into waterway, and there are measures one can take to do that, specifically injecting cations if there's potential for things to move. But Petrofix is designed in such a way, both intentionally and maybe some non-intentionally, that it doesn't move all that far in the subsurface. So that can be a positive if you have a site like that next to a waterway.
Yeah, so Petrofix becomes positionally stable after a period of weeks and months. It will not move anymore. You will never get it out of the ground. The electron acceptors are water soluble. By the way, you have the choice to apply or not apply the electron acceptors. It's optional. We just feel that if you can do bioremediation, you should do bioremediation with them.
ORC, oxygen releasing compound, can also be injected with Petrofix, not just co-applied though.
That's a good point.
And for certain sites that have high concentrations, that's something that we commonly do.
Right. And I would ask consult with me, but you can use Petrofix, and say ORC or other combination of electron acceptors you might feel comfortable with can be paired with it. It doesn't even have to be what we provide. There are some that are not compatible with the material. So just reach out to me if you have any questions about it.
Okay. Has directional drilling ever been used for injecting?
It's a really good question. Not with Petrofix. We've done it with Plume Stop. So our other liquid activated carbon product. Yes. The only concern I have with directional drilling is discrete delivery. If you can ensure discrete delivery into the zones with directional drilling, I have no issue with you putting Petrofix in there. I think it would be a great application.
Okay. Someone states, I imagine that metabolites could become water soluble. Have you checked for that? And if so, is it even a problem?
I'm not sure what metabolics means. So
Metabolites?
I apologize, I may not be able to answer that question. I don't know if he means by intermediates, perhaps. I'm not really sure.
Sugars, like maybe the other electron acceptors, any sort of sugar or something like that.
So yeah, so whereas the Petrofix eventually will be positionally stable, the electron acceptors will generally.
Sorry, the byproducts of biodegradation.
Byproducts, okay. That's yeah, certainly true that as you start breaking down the rings, it's going to change their solubility. It's going to change their retardation rates. You can get some of that. That hasn't been something that's really been a concern or we really looked at. I'm not saying it's not a concern, but we haven't really looked into that a tremendous amount.
To make a comparison, this is something we look deeply at for PFAS or chlorinated sites, and realistically, where it comes into play is something that where you would want to contact us anyway is fast-moving groundwater. Say you have a site, if it's chlorinated and you're putting in a plume stop barrier with CVI or something like that, and you're worried that vinyl chloride or some of the other compounds may not that aren't absorptive may come off. Typically, what we do is we'll model how much activated carbon there is versus how quickly groundwater is moving, and the only time it becomes a factor is if groundwater is moving excessively fast. But I haven't heard of it.
Yeah, most
Petrofix sites.
Most intermediates, like I'm trying to think to myself, like say all the intermediates from say just an alkane or whatnot. I mean, they certainly will soar up to carbon, and so that will happen. But it's interesting. We haven't looked at that. Like as Andrew said, we look at that a lot actually for solvents when you're looking at PC, going to TC, DC, vinyl chloride, et cetera, or PFAS. It's never been a requirement to really look at for hydrocarbons. So I don't have more information on that.
Okay, that looks like it for questions. Again, to everyone, thank you. Presentations will be available later today at isa.org/webinars. Thank you to Site. Thank you to today's sponsor, who I forgot to mention off the top, SNC Lavalin. Thank you to them for making today possible. And the sponsors keep these free, so that helps everybody in these times. A reminder about Envirotech. ISA would really appreciate your support. Thank you again, Todd and Andrew and Regenesis, for doing this today, and we really appreciate it. Thank you, everyone. Stay safe.
Thank you, Joe. Thanks, everybody.
Thank you, Joe. Thank you, everyone. Take care.